so far in this course, we've been talking a lot about data abstraction. And remember, the idea is that we build systems that have these horizontal barriers in them, these abstraction barriers that separate use, the way you might use some data object, from the way you might represent it. Or another way to think of that is up here you have the boss who's going to be using some sort of data object, and down here is George, who's implemented it. Now, this notion of separating use from representation so you can think about these two problems separately is a very, very powerful programming methodology, data abstraction. On the other hand, it's not really sufficient for really complex systems. And the problem with this is George. Or actually, the problem is that there are a lot of Georges. Let's be concrete. Let's suppose there's George, and there's also Martha. Okay, now George and Martha are both working on this system, both designing representations, and absolutely are incompatible. Right? They wouldn't cooperate on a representation under any circumstances. And the problem is, you would like to have some system where both George and Martha are designing representations, and yet, if you're above this abstraction barrier, you don't want to have to worry about that, whether something's done by George or by Martha, and you don't want George and Martha to interfere with each other. Somehow, in designing a system, you not only want these horizontal barriers, but you also want some kind of vertical barrier to keep George and Martha separate. Well, let me be a little bit more concrete. Imagine that you're thinking about personnel records for a company, a large company with a lot of loosely linked divisions that don't cooperate very well either. And imagine that, imagine even that this company is formed by merging a whole bunch of companies that already have their personnel record system set up. And imagine that, once these divisions are all linked in some kind of very sophisticated satellite network, and all these databases are put together. And what you'd like to do is, from any place in the company, be able to say things like, what's the name in a personnel record? Or what's the job description in a personnel record? And not have to worry about the fact that each division obviously is going to have completely separate conventions for how you might implement these records. From this point, you don't want to know about that. Well, how could you possibly do that? One way, of course, is to send down an edict from somewhere that everybody has to change their format to some fixed compatible thing. That's what people often try, and of course it never works. Another thing that you might want to do is somehow arrange it so you can have these vertical barriers, so that when you ask for the name of a personnel record somehow, whatever format it happens to be, name will figure out how to do the right thing. You want name to be so-called a generic operator. Generic operator means what it sort of precisely does depends on the kind of data that it's looking at. More than that, you'd like to design the system so that the next time a new division comes into the company, they don't have to make any big changes in what they're already doing to link into this system, and the rest of the company doesn't have to make any big changes to admit their stuff to the system. Right, so that's the problem you should be thinking about. You'd like it sort of just to work. You want to be able to include new things by making minimal changes. Okay, well, that's the problem that we're going to be talking about today. And you should have this sort of distributed personnel record system in your mind, but actually the one I'll be talking about is a problem that's a little bit more self-contained than that. that'll bring up the issues, I think, more clearly. That's the problem of doing a system that does arithmetic on complex numbers. So let's take a look here. Just as a little review, there are things called complex numbers. A complex number you can think of as a point in the plane, or z, and you can represent a point either by its real part and its imaginary part. So if this is z, then its real part is this much, and its imaginary part is that much. And you write z equals x plus iy. Or another way to represent a complex number is by saying what's the distance from the origin and what's the angle. So that represents a complex number as its radius times an angle. This one's called, the original one's called rectangular form, rectangular representation, real and imaginary part, or polar representation, magnitude and angle. And if you know the real and imaginary part, you can figure out the magnitude and angle. If you know x and y, you can get r by this formula, square root of sum of the squares, and you can get the angle as an arctangent. Or conversely, if you knew r and a, you could figure out x and y. X is r times the cosine of a, and y is r times the sine of a. Right, so there's these two, they're complex numbers. You can think of them either in polar form or rectangular form. What we would like to do is make a system that does arithmetic on complex numbers. In other words, what we'd like, just like the rational number example, is to have some operations plus c, which is going to take two complex numbers and add them and subtract them and multiply them and divide them. Okay, well, there's a little bit of mathematics behind that. What are the actual formulas for manipulating such things? And it's sort of not important where they come from, but just as an implementer, let's see. You can think, if you want to add two complex numbers, it's pretty easy to get its real part and its imaginary part. The real part of the sum of two complex numbers, right, the real part of the z1 plus z2 is the real part of z1 plus the real part of z2. Okay? And the imaginary part of z1 plus z2 is the imaginary part of z1 plus the imaginary part of z2. Right, so it's pretty easy to add complex numbers. You just add the corresponding parts and make a new complex number with those parts. If you want to multiply them, it's kind of nice to do it in polar form, because if you have two complex numbers, the magnitude of their product is here the product of the magnitudes, and the angle of the product is the sum of the angles. So that's sort of mathematics that allows you to do arithmetic on complex numbers. Let's actually think about the implementation. Well, we do it just like the rational numbers. Right, we come down, we assume we have some constructors and selectors. What would we like? Well, let's assume that we make a data object, cloud, which is a complex number that has some stuff in it, and that we can get out from a complex number the real part, or the imaginary part, or the magnitude, or the angle. We want some ways of making complex numbers, not only selectors but constructors. So we'll assume we have a thing called make rectangular. What make rectangular is going to do is take a real part and an imaginary part and construct a complex number with those parts. Similarly, we can have make polar, which will take a magnitude and an angle and construct a complex number which has that magnitude and angle. So here's a system. We'll have two constructors and four selectors. And now, just like before, in terms of that abstract data, we'll go ahead and implement our complex number operations. And here you can see translated into Lisp code just the arithmetic formulas I put down before. Right? If I want to add two complex numbers, I will make a complex number out of its real and imaginary parts. The real part of the complex number I'm going to make is the sum of the real parts. The imaginary part of the complex number I'm going to make is the sum of the imaginary parts. I put those together, make a complex number. That's how I implement complex number addition. Subtraction is essentially the same. All I do is subtract the parts rather than add them. To multiply two complex numbers, I'll use the other formula. I'll make a complex number out of a magnitude and angle. The magnitude is going to be the product of the magnitudes of the two complex numbers I'm multiplying. And the angle is going to be the sum of the angles of the two complex numbers I'm multiplying. So there's multiplication, and then division. Division is almost the same. Here I divide the magnitudes and subtract the angles. Okay. All right, well, now I've implemented the operations. And, well, what do? We call on George. Right, we've done the use. Let's worry about the representation. We'll call on George and say to George, go ahead and build us a complex number representation. Well, that's fine. George can say, we'll implement a complex number simply as a pair that has the real part and an imaginary part. So if I want to make a complex number with a certain real part and an imaginary part, I'll just use const to form a pair, and that's George's representation of a complex number. So if I want to get out the real part of something, I just extract the car, the first part. If I want to get the imaginary part, I extract the coulter. How do I deal with the magnitude and angle? Well, if I want to extract the magnitude of one of these things, I get the square root of the sum of the square of the car plus the square of the coulter. If I want to get the angle, I compute the arctangent of the coulter in the car. And this is a Lisp procedure for computing arctangent. And if somebody hands me a magnitude and an angle and says, make me a complex number, well, I compute the real part and the imaginary part, r cosine of A and r sine of A, and stick them together into a pair. Okay, so we're done. In fact, what I just did conceptually is absolutely no different from the rational number representation that we looked at last time. It's the same sort of idea. You implement the operators, you pick a representation, right? Nothing different. Now, however, let's worry about Martha. See, Martha has a different idea. She doesn't want to represent a complex number as a pair of a real part and an imaginary part. What she would like to do is represent a complex number as a pair of a magnitude and an angle. So if instead of calling up George, we asked Martha to design our representation, we'd get something like this. We'd get make polar. Sure, if I give you a magnitude and an angle, we're just going to form a pair that has magnitude and angle. If you want to extract the magnitude, that's easy. You just pull out the car or the pair. If you want to extract the angle, sure, that's easy. You just pull out the coulter. If you want to look for real parts and imaginary parts, well, then you have to do some work. If you want the real part, you have to get r cosine A. In other words, r, the car of the pair, times the cosine of the coulter of the pair. So this is r times the cosine of A, and that's the real part. If you want to get the imaginary part, it's r times the sine of A. And if I hand you a real part and an imaginary part and say, make me a complex number with that real part and imaginary part, well, I figure out what the magnitude and angle should be. And the magnitude's the square root of the sum of the squares, and the angle's the arctangent, and I put those together to make a pair. All right, so there's Martha's idea. Well, which is better? Well, if you're doing a lot of additions, probably George's is better because you're doing a lot of real parts and imaginary parts. If mostly you're going to be doing multiplications and divisions, then maybe Martha's idea is better. Or maybe, and this is the real point, you can't decide. Or maybe You just have to let them both hang around for personality reasons. Right? See, maybe you just really can't ever decide what you would like. And again, what we would really like is a system that looks like this. That somehow there's George over here who has built rectangular complex numbers. And Martha, who has polar complex numbers. And somehow we have operations that can add and subtract and multiply and divide. And it shouldn't matter that there are two incompatible representations of complex numbers floating around this system. In other words, not only we'd like an abstraction barrier here that has things in it like real part and imaginary part and magnitude and angle. So not only is there an abstraction barrier that hides the actual representation from us, but also there's some kind of vertical barrier here that allows both of these representations to exist without interfering with each other. And the idea is that the things in here, real part, imaginary part, magnitude, and angle, will be generic operators. If you ask for the real part, it will worry about what representation it's looking at. Okay, well, how can we do that? There's actually a really obvious idea if you're used to thinking about complex numbers, if you're used to thinking about compound data. Right? See, suppose you could just tell by looking at a complex number whether it was constructed by George or Martha. In other words, so it's not that what's floating around here are ordinary, just complex numbers, right? They're fancy designer complex numbers. Right? So you look at a complex number, it's not just a complex number, it's got a label on it. It says this one is by Martha. Right? Or this is a complex number by George. Right? They're signed. See, and then whenever we looked at a complex number, we could just read the label, and then we'd know how you expect to operate on that. In other words, what we want is not just ordinary data objects. We want to introduce the notion of what's called typed data. Right? Typed data means, again, there's some sort of cloud, and what it's got in it is an ordinary data object like we've been thinking about. It's sort of, we call that the contents, sort of the actual data, but also a thing called a type. Right? It's signed by either George or Martha. So we're going to go from regular data to typed data. How do we build that? Well, that's easy. Right? We know how to build clouds. We can build them out of pairs. So here's a little representation that supports typed data. There's a thing called take a type and attach it to a piece of contents, and we just use const. And if we have a piece of typed data, we can look at the type, which is the car. We can look at the contents, which is the cooter. Now, along with that, the way we use our typed data is we'll test, when we're given a piece of data, what type it is. So we have some type predicates with us. For example, to see whether a complex number is one of George's, whether it's rectangular, we just check to see if the type of that is the symbol rectangular. Right, the symbol rectangular. And to check whether a complex number is one of Martha's, we check to see whether the type is the symbol polar. Right, so that's a way to test what kind of number we're looking at. Now let's think about how we can use that to build the system. So let's suppose that George and Martha were off working separately, and each of them had designed their complex number representation packages. What do they have to do to become part of the system, to exist compatibly? Well, it's really pretty easy. Remember, George had this package. Here's George's original package, or half of it. And underlined in red are the changes he has to make. So before, when George made a complex number out of an x and a y, he just put them together to make a pair. And the only difference is that now he signs them. He attaches the type, which is the symbol rectangular, to that pair. Everything else George does is the same, except that, see, George and Martha both have procedures named real part and imaginary part. So to allow them both to exist in the same Lisp environment, George should change the names of his procedures. So he'll say, this is George's real part procedure. It's the real part rectangular procedure. The imaginary part rectangular procedure. And then here's the rest of George's package. Right? He had magnitude and angle, just renames the magnitude rectangular and angle rectangular. And Martha has to do basically the same thing. Martha, previously, when she made a complex number out of a magnitude and angle, she just consts them. Now she attaches the type polar, and she changes the name so her real part procedure won't conflict in name with George's. Right, so real part polar, imaginary part polar, magnitude polar, and angle polar. Okay. Now we have the system, right? There's George and Martha. And now we've got to get some kind of manager to look at these types. See, how do these things actually going to work now that George and Martha have supplied us with typed data? Well, what we have are a bunch of generic selectors. Right? Generic selectors for complex numbers, real part, imaginary part, magnitude, and angle. And let's look at them more closely. What does real part do? If I ask for the real part of a complex number, well, I look at it. I look at its type. I say, is it rectangular? If so, I apply George's real part procedure to the contents of that complex number. Right, this is a number that has a type on it. I strip off the type using contents and apply George's procedure. Or, is this a polar complex number? If I want the real part, I apply Martha's real part procedure to the contents of that number. So that's how real part works. And then similarly, there's imaginary part, which is almost the same. Right? It looks at the number, and if it's rectangular, uses George's imaginary part procedure. If it's polar, uses Martha's. And then there's a magnitude and an angle. Right? So there's a system, has three parts. There's sort of George and Martha and the manager. And that's how you get generic operators implemented. Let's look at just a simple example, just to pin it down, of exactly how this is going to work. See, suppose you're going to be looking at the complex number, say, whose real part is 1 and whose imaginary part is 2. So that would be 1 plus 2i. Well, what would happen is up here above, where the operations have to happen, that number would be represented as a pair of 1 and 2 together with typed data. That would be the contents, and the whole data would be that thing with the symbol rectangular added onto that. And that's the way that complex number would exist in this system. When you went to take the real part, the manager would look at this and say, oh, it's one of George's. He'll strip off the type and hand down to George the pair 1, 2. And that's the kind of data that George developed his system to use. Okay, so it gets stripped down. Later on, if you ask George to construct a complex number, George would construct some complex number as a pair, and before he passes it back up through the manager, would attach the type rectangular. So you see what happens. There's no confusion in the system. It doesn't matter in the least that the pair 1, 2, means something completely different in Martha's world. In Martha's world, this pair means the complex number whose magnitude is 1 and whose angle is 2. And there's no confusion because by the time any pair like this gets handed back through the manager to the main system, it's going to have the type polar attached, whereas this one would have the type rectangular attached. Okay, let's take a break.